For All right. We are moving on with the main event tonight. It sounds a little loud. I will lower my microphone. All right, everybody. We are going to have the next installment of Astronomy on tap. We're going to have Astronomy in the news with our resident Astronomy in the News anchors, Caleb Gamar and Jasmine Singh. Y'all are going to talk at the same time, so pass it on. Over to you.
Well, good evening, everyone. All right, good, yeah, all right, there we go. Okay, good. Okay, once again, my name's Caleb Gamar.
I'm Jasmine Singh.
And we are your astronomy news presenters this evening. So, first and foremost, May night sky sights. All right, so for those of you that like to go outside and actually observe what is visible in the heavens, this is what will be there. So this is, of course, the dome of the sky overhead. You are looking at a perfect springtime sky. Yes. All right. And what really marks that perfect springtime sky is a constellation of Leo the Lion right here. Find the backwards question mark shape and the bright star Regulus. That backwards question mark shape marks the head, the mane, the chest, and Regulus, the heart of Leo the Lion. And then there's this little triangular shape back end right there. Now, if you have a little trouble finding Leo the Lion, don't worry. There's an even more familiar group of stars there. It's right here. Can anyone tell me what that is? Big Dipper, or Ursa Major, actually, is a more appropriate constellation. Yep. So follow the front two stars of the Dipper on down, and they lead to Regulus. Follow them up, and they lead to the North Star, Polaris. Follow the arc of the Dipper, and it arcs this nice yellow-orange star called Arcturus. And then if you spike straight down to the brightest blue star you find, that is Spica. So arc to Arcturus, and spike to Spica. Arcturus is actually what our own sun will become in about 4.5 billion years. It'll become a red giant star. Arcturus is indeed a red giant star. Now, as you look over toward the western part of the sky, you will see the very bright visible planets Jupiter and Mars starting to make their way closer and closer to the horizon. During much of the month, Jupiter will be very close to the horizon, so make sure you get a good look at that before it starts setting with the sun in the sky. And then, of course, Mars is still very well visible over there in the sky. It's actually right in the constellation of Cancer there between Leo and the wintertime constellation of Gemini. So again, those are the planets. Make sure you get your look at them before they go away. Now, if you have a pair of binoculars, I hate to tell you this, it's kind of a barren night sky right now. And the reason why is because you're actually looking out of the plane of our galaxy into distant intergalactic space. But the great thing about that is you are in the prime season for looking at galaxies. And there are a few that are bright enough to see with binoculars under a very, very dark nighttime sky. So get away from the city lights, go outside, look for Ursa Major there, and right toward the front of Ursa Major there, the head of the bear right there, just look a little above with a pair of, really ideally about a 20 by 80 pair of binoculars, but 10 by 50s will work. And you'll see a couple of these little gray smudges there. Those are the galaxies M81 and M82. Those are some very nice galaxies, about 12 million light years away. So you were looking at them as they appeared about 12 million years ago through the binoculars. They actually are both close enough to each other that they are gravitationally interacting. So take a look up online about those galaxies, get some more information, and go out and observe them. Very, very fascinating stuff. One more note. There's this nova that is supposed to happen eventually. T Corona Borealis. So if you find the constellation of Boötes, the herdsman, again, follow the arc to Arcturus. Arcturus is part of that kite-shaped constellation. Right next to that kite-shaped constellation is this kind of bowl-shaped constellation. That's Corona Borealis. And just off this end of the bowl right there is about where T Corridor is. It has not erupted yet, but it is on a roughly 80-year time span cycle of this nova eruption taking place. Keep watching. It should be sometime during this year, maybe next year, but we'll see what happens. So when this does happen, though, do understand you have to know what you're looking for. It will only become as bright as the North Star there, which is bright, but not horribly bright. You do have to know what you're looking for. But nonetheless, though, do watch out for that over the next few months. And we'll go ahead with our first news story. So, Jasmine?
All right. Okay, so the Lucy spacecraft has taken images of its second asteroid destination. So it passed about 600 miles from the Maybell asteroid. That name, I'm not going to try to say it. And then the Johansson, yes. Okay. Yeah, and it's the second asteroid. It'll be the third if Dinkinesh and Selim are counted as two, visited by the mission. And so the next stop is going to be the Trojan asteroids. There are about 8 planned. So that's really cool.
All right, and so for the next story, a rather odd exoplanet discovery. The astronomers have actually discovered an exoplanet that is orbiting perpendicularly to the star system that's in. So there's this nice brown dwarf star here, I should say, 2M1510AB. Looking at the way these stars moved using the Very Large Telescope, there's an instrument on that called the ultraviolet shell spectrograph, ultraviolet visible shell spectrograph, and they could look at little differences in the way the spectral lines, the little lines that indicate what the star is made of, essentially. They could see how these lines shifted, and they noticed something kind of funny about the motion of these lines. And so you have what is probably a planet in an orbit like you see there between the two binary stars. So you have one star, the other star kind of circling around in that figure 8 pattern there, and then the vertically oriented orbit of the odd exoplanet. Now, this system on its own is also one of the more interesting objects in the sky. It is only the second of its kind of this binary brown dwarf system ever discovered. So really, really fascinating stuff from the Very Large Telescope.
All right, and in more James Webb news, James Webb has observed the oldest spiral galaxy yet found. So you can see about right here, and it's zoomed in over here. So it's observed as it appeared about 12.5 billion years ago. So in the grand scheme of the universe, that's like pretty early on. And it's named Zhulong, which means torch dragon in Chinese mythology. And this galaxy type is extremely rare to look back at. So it's just kind of crazy that we can see with James Webb, galaxies that are like pretty young comparatively to everything else. Like we're literally looking back at pretty much the beginning of the universe. I know 1 billion years is like a lot of time, but in the grand scheme of things, in the age of the universe, that's pretty young considering it's about 13-ish billion years old. So really cool stuff.
And then one more news story. So how many of you have heard of this space instrument, I should call it, called NICER? How many of you have ever heard of it? A few of you? Okay, all right. It's a really interesting instrument. It is on board the International Space Station. It stands for Neutron Star Interior Composition Explorer. It's a really fascinating mission. You can actually see the telescope array itself in the visor reflection of the astronaut here. They did some maintenance on this not too long ago to keep it operating as time goes on. And this particular instrument has been used to observe what is called a quasi-periodic eruption, an X-ray quasi-periodic eruption. Now, what on earth is this? Well, this is a periodic flaring of an X-ray source over a short period of time, a few-day period of time. And in this little galaxy right here, which is about 300 million light years away, by the way, there was observed not too long ago a sudden brightening. And then using NICER, they've actually been able to do follow-up observations and see that, oh, this is one of these QPEs, these quasi-periodic eruptions. So what's probably happening here is there's a star, very active star, that's orbiting around a supermassive black hole near the center of this galaxy. And as a star goes through the disk of material around the black hole, it actually impacts material and causes these X-ray flares to happen periodically. And this is one of only, I think, one of only 12 of these things that have been discovered so far, at least the 12th of only a few that have been discovered so far. So really, really fascinating object out there, and a great discovery by this rather uncelebrated space observation device called NICER. So just a few things to keep watching out for over the next few weeks. We do have a Friday night celestial lights observing at the UTSA Observatory this Friday night. The weather should be great, so please join us. Top floor of the Flown Science Building. Look us up online, UTSA Observatory, can't miss it. So again, please do join us. That will be the last one for the year, by the way, until the school year starts again in August, so do bear that in mind. We probably will do another South Yonah River State Park observing, but we haven't quite determined the time for that yet, so we'll get that information out eventually. In terms of SAAA, San Antonio Astronomical Association, every Wednesday at sunset, there's observing at Raymond Remkus Park. If we have any of those folks in the room tonight, I'm not seeing, well, I think I see a couple of you out there. Yep, there you go. Anyway, please ask them, because I know I probably missed some things in their calendar doing this. Okay, all right, yep. So, so again, just ask him. He'll be able to tell you more about that. And then Scobie Planetarium, they're doing shows on the 9th, 16th, 23rd, and 30th. Doors open at 6 p.m. And again, I didn't see on the calendar, but I think there's probably one of those Friday observings there. Usually first Friday. Yeah. Okay, so now for the last images.
All right, we always like to end off on some pretty images just to show you what's out there, what we've been looking at. So Hubble just recently looked at NGC 1961, and to me that's a very beautiful picture. It looks like a painting, so I just really like to look at that one. And this one actually very fitting for Kylie's talk. This is actually currently the highest resolution image of the sun taken by the solar orbiter, so kind of goes with your talk. And then we got NGC 1514 from JWST. So we're out there taking beautiful images, and we will always make sure that you see them. But do look these up and try to look at them online, because the resolution is a lot better, and I like to zoom in as far as the eye can see, especially on the James Webb images. Just keep on zooming in. It's quite beautiful, actually. So, yeah. Thank you.
Once again, thank you very much. That's Astronomy News.
All right. Our next presentation is recent Dr. Adeloye. Close enough. What? Is this? Oh, boy. Okay, there we go. Okay. Is that a Manchester United polo? Crazy. You come. Anu is born in Nigeria, but landed in America in Alfred, New York. Does anybody know Alfred, New York? Small town in New York. Okay. All right. Wow. Where he went to Alfred University, and there's apparently an Alfred State University, so this small town has two universities named after itself. But then he came to University of Texas, Austin, where he drove from today, where he got his PhD in aerospace engineering, studying, there we go, Io's plumes, but I'll let him take it away. He did not know his drinking word until probably right now, so let's see what it is.
All right. Well, thank you everyone for showing up.
Down arrow is to advance.
Okay, thank you. So I think my drinking word is going to be brightness. Let's see how many times I can bring it up. But so the title of the talk today is Blown Away by Io, Modeling Tvashtar's Plume, and Dreaming of a Sample Return. And this work has been done throughout my PhD and is sponsored by a NASA grant under the New Frontiers Data Analysis Program. And most of our computations at UT Austin were done at our Texas Advanced Computing Center, the supercomputers up there. So as an introduction, Io is one of the 4 Galilean moons of Jupiter. It is the innermost one, and it stands out as the most volcanically active celestial body in our solar system. There's hundreds of volcanoes that are active, and that gives it the unique coloration that you see here. It's one of the most beautiful things I've seen. Oh, wow. So the source of Io's volcanism is as a result of tidal eating due to kind of like push and pull as it interacts gravitationally with Jupiter and also with the neighboring Galilean moons. So if you imagine a kind of tug of war between Jupiter and the other moons with Io at the center, it kind of makes sense that Io would be a little angry, right? So that allows it to spew out stuff, gas, dust, and it's been doing it for so long. The first time Galileo discovered Io in the 17th century, but the first time we got a really close-up look at Io was during the Voyager 1 and Voyager 2 missions. And before Voyager came close to Io, the idea was that we thought Io was a dead planet, kind of like our moon, but that couldn't have been farther from the truth, right? When Voyager came around, they saw that there were a lot of volcanic activity. You can see this eruption here producing a plume that's about 350 kilometers high. So if we had something this high on Earth, the International Space Station would kind of just graze over it. All right. There were other eruptions, kind of like at Prometheus here at Mazda, Ra, Gibel, and so on. And this was kind of revolutionary at the time, right? The next time that we would fly around Jupiter and look at Io was when the Galileo spacecraft did its flyby. And this time, about 20 years later, Galileo found that surprisingly there had been surface changes at Io, meaning that as materials have been coming up, being spewed out due to volcanic activity, there's been emplacement of old material by new material, and there's been short and long-term changes. For instance, you can see in the short term between, wow, this is missing, but this is September of 1997, right? Between April of 1997 and September, just a period of a few months, you can see some changes on the surface, and also changes on the surface in a space of about 2 years. And Prometheus, which is another volcanic site on Io, between the 20 years at its lava flow from this point about 80 kilometers west. So there's like significant change on Io, and because of this significant change, there's like the materials on Io are not subject to space weathering. So if we were to, go to Io, collect sample of it, you would see materials that have been preserved in their original state as they were, maybe even up to a couple of millions of years back. But really, what blew our minds away was during the New Horizons flyby in 2007. New Horizons, if you know, is a spacecraft that was originally sent out to observe Pluto and Charon. But in 2007, it did a flyby of the Jovian system, kind of like a gravity support. And during a period of like 3 to 4 days, as it was doing the flyby as shown in this movie over here, it observed Io and many of the moons around Jupiter. And at Io, it found that there was an active volcanic eruption near the North Pole at Tvashtar. Now, what was most surprising about this eruption was that as the solar phase angle, which I will call phi here, and it's plotted here on the x-axis against the radiance, which is a measure of the brightness. And as the solar phase angle increased from just under 40 degrees to just above 150 degrees, the brightness of Tvashtar's plume, which is the region within these blue ellipses of the top of the canopy of the plume, it's about 350 kilometers high, increased significantly, irregularly, and by over an order of magnitude. And this was surprising, unexpected, and the kind of main focus of my PhD was to answer the question, why does brightness increase? So, like I said, the objective was to answer the question why, the objective is to unravel the different physical mechanisms that could be active within the plume that could have driven the brightness change throughout the flyby. And to do that, I was able to enhance the physical models that we've used to model Ionian plumes over the years, use that to assess volcanic source activity, and also to been able to investigate optical scattering properties of the plume using mean theory and ray tracing coupled with CFD methods. So the method, the CFD method is direct simulation Monte Carlo. It's DSMC for short. It is a stochastic method whereby rather than solve a bunch of equations like the Navier-Stokes or the Boltzmann equation, we actually simulate the actual particles, gas and grains or dust of different sizes. And the gas and grains in this case exit out of a huge vent, which is about 3 kilometers in radius. And we modeled them because they go from very relatively high pressures, which is about a millionth of an atmosphere, right? But for Io, this is relatively collisional. And as the gas expands into vacuum, they go into what we call kind of free molecular. And because of the changing scales of changing flow scales, we have to model the flow in different stages. So material goes out of stage 1, which is about 6 kilometers by 6 kilometers. So material goes out of here, and as they go out and the flow is at steady state of gas and dust, we collect all of the materials that go out into stage 2, into stage 3, and finally into what we have here is stage 4. At the top of stage 4, you have what we call at the top of stage 4, we have what we call a free molecular cell that allows material to go up and then fall back under gravity until you eventually form the plume as we have it here. Let it form. All right, so what we have here is a shock canopy that's formed as rising molecules kind of collide with falling molecules. So they get shocked, they cancel out their vertical momentum, and then slide off to form this umbrella shape that you can see here. So using UT's supercomputing resources, we were able to construct realistic plume models of Tvashtar's plume during the flyby. The first step to now compare with what was actually captured by the Lorry camera, which was on board New Horizons, was to process the original images that were taken. This is one of such images, this is a raw image that was taken about a solar phase angle of 110 degrees. So processing the image, we're able to extract the coordinates of the center of the plume, the center of the planet, and we're able to, after that, kind of construct a DSMC column density image, whereby originally we computed simulation within a 1 degree slice. We're able to revolve it around 360 degrees. And then from the viewpoint of the spacecraft, we're able to kind of compute images of what the spacecraft would have seen. So the final image then looks like this, which we can compare with the original images, and we overlay and see that actually our features match. We match the location of where the plume originates from, and other features on the planet, kind of like the terminator, which is where the sun kind of cuts off and you have night side. We also are able to match that with processing of our DSMC data. One of the things that we thought was driving the brightness change during the I gotta get used to that. One of the things that was driving the brightness change was changing observational geometry during the flyby, right? As over the period of 3 to 4 days, EO completed about over 2 full revolutions around Jupiter, and this resulted in different viewing geometries. So there's some times when the plume is on the near side, day side, or it's on the near side and the night side. So when near side, that means we can see like a really odd spot here, which is kind of like marked out by the longitude and latitude by this red dashed lines, and same thing here. And you can see a different part of the plume. And at other times, it's on the far side, right? And part of EO is actually blocking the plume. And it could be on the far side, day side, or the far side, night side. So over the period of the flyby, we are looking at different parts of the plume. So the question was then, could this have influenced the brightness that was seen? So to answer that, again, we use DSMC simulation results. This time, when we construct our column densities, we take into account the effects of shadow. So take in results of DSMC which have simulated different types of grain sizes. So we're able to simulate grains that go all the way from 20 nanometers all the way to 10 microns. But we take into account the fact that some of these grains could be in shadow. They could be in shadow of the planet, or they could be on the other side of the planet where we cannot see them. So what are the column densities that result from that? This is shown for about 3 different epochs, but in total we have 25 different observational points. So again, within the same regions where we compute the brightness of the plume, we compute the column densities, which is pretty much the amount of particles of the different sizes that you can see along your line of sight in a particular region of the plume. And we find that when we compare this, so on the left-hand side, I have normalized column densities plotted against solar phase angle. On the right y-axis, I just have the normalized radiance. We can see that across the flyby, right, while the radiance increases by about an order of magnitude, note that this is on a log scale, while this is on a linear scale, there isn't a comparative 10 times sort of magnitude increase in the column density. So that kind of indicates that the column density isn't the source, changes in the column density or in the observational geometry that determines how much of the plume we can see, or how much of the plume the spacecraft can see, is not the main determinant of how the brightness increased. However, right, if you look at this, you can see that there's similar changes, right? An increase followed by a decrease, then similar irregularities here and here, whereby the changes in the column densities match the changes that we've seen in the brightness profile. And so this leads to the conclusion that the viewing geometry played a role in affecting how much of the plume that could be seen, and that because of things I haven't really explained in this talk, the larger grains were obscured, meaning that when the geometry was more complicated, or the plumes were on the other side of EO, or maybe on the night side of EO, we could not see the larger grains. And if you know, larger grains scatter more light, so they appear brighter, all right? And the fluctuations in the column density profiles kind of correlate with the fluctuations in the brightness profile. And so this means that the changes that were seen, or the irregularities that were seen in the brightness profile, must have been due to changes in the spacecraft geometry rather than the evolution of the plume itself. The next step after that is looking at the scattering properties of the grains in the plume. And this is done using me theory. In our DSMC simulations, we're able to simulate different grain sizes that could be present in the plume, from nanoscale all the way to micron scale grains. And it is possible that if a small grain scatters less light than a bigger grain would scatter. And if they're in different populations in the plume, then depending on how much of those grains you have in the plume, you could scatter more light or less light. And so it is important that to be able to understand how the plume scatters light as a whole, you understand how each individual small grain scatters light. And this is what we do here, where we kind of model using me theory what the scattering profile will look like in back scattering, side scattering, or forward scattering. And at the end, we find that with this profile, each grain size matters, right? While the smaller grains, which are in a much larger population, they don't really display a forward scattering, with the brightness staying kind of like, with the brightness kind of staying consistent during the flyby. But the bigger grains scatter more light, and you can see that as the size of the grains increase, the scattering profile also shows an increase in the scattering of the grains. Now, the next step after we've looked at how each individual grain scatters light is to combine it with our DSMC modeling. So, and that is done with this equation I've put up here, where we take the number density of the grains from DSMC computations, cell volume data also from DSMC computations, and cross-sectional area data also from DSMC computations. And we are able to construct radiance images, which kind of represent the brightness of the plume, of each of the different grain sizes. In this case, we have 9 different grain classes that span the log normal grain size kind of distribution that is present in the plume. And doing that for each grain size, so from very small grains, which is about 20 nanometers to 120 nanometers, to about 7.5 microns to 10 microns at the last grain size. Then after we're able to construct the individual radiance profiles, combining DSMC and me theory, we sum up all these results to get an overall radiance profile. And this overall radiance profile can be compared with the actual image that was taken by New Horizons. So previous works have shown that there are different types of grain size distributions that could be used to model Ionian plumes, especially of this size, which is a Pele type. And we use 2 of those nominal grain size distributions. One is a bimodal, the other is a unimodal plume. And we also define what is called a reduced chi-squared value, which compares the radiance profiles from what the Lorry camera recorded versus what we get from either of the grain size distributions that are simulated using DSMC. And we find that, as you can see here, the key to understanding the reduced chi-squared profile is that when it's approximately 1, we have a good fit. When it's much greater than 1, it's a poor fit, and when it's much less than 1, that means we've overfit the data, and we would have to go back to the drawing board, so to speak. But for these 2 cases, we can see that there is kind of like a good amount variation between how the 2 grain size distributions vary. And when I say the grain size distributions vary, I mean that there might be more smaller grains than bigger grains when you compare the 2 grain size distributions. And while both grain size distributions show kind of poor fits, we can see that each simulated distributions shows about a 10 times increase in the brightness profile across the flyby. And the 10 times increase in the brightness can be associated to forward scattering of the grains, right? As I showed earlier, the grains that are bigger tend to like scatter light in a more forward direction. And so depending on how much of those grains you have relative to grains that do not scatter light the way you want it to or the way you expect it to, that could affect the brightness profile that is seen. So the results I am showing here actually underpredict the observed plume brightness with the unimodal grain size distribution. However, we've been able to show, which would probably take me 30 more minutes to explain, but we've been able to show that if we change the grain size distribution via a comprehensive parametric study, we're able to replicate the observed distribution and the observed brightness of the plume that was observed in 2007. So in conclusion, we were motivated by a 10 times increase in the brightness of Tvashtar. And to answer that question of why there was that increase, we enhanced our DSMC modeling, integrating different physical models. We were then able to show that forward scattering is the kind of chief factor affecting the flyby. And assuming our current models assume steady state, whereas there are other models that could be present in the plume that are not considered yet, and our future work would actually look at that. And we believe that this work provides a refined framework for interpreting spacecraft observations, especially on bodies that have volcanism like Io, Enceladus, and other bodies across our solar system. And I have chosen to end with this simulation here, which shows Tvashtar's plume. If you had an observer that was rotating around Tvashtar at about 3 million kilometers away. So the question that this kind of aims to answer is, if I were to look at Tvashtar, maybe from Earth, maybe from a distant observer, maybe from an observer that's actually approaching Tvashtar, what would I see? If I were to, fly to Tvashtar to collect material, which is actually some a concept mission in development, what would we see? And so this sample return missions are kind of like the holy grail of next level of NASA missions or spacecraft missions. And with these, with this tool as a possibility, we can predict for Ionian plumes, if we were to visit them, what we can see and what we can return, where it's safe for a spacecraft to fly, and so on. And with that, thank you very much, and I'll be happy to take your questions.
Thank you so much for that. Sorry. I was in the middle of eating, so bear with me here. Right. The first question is, on Io, what do the different colors of the surface indicate from those images you showed?
So there's multiple species of gas and dust that are present on Io. The black is mostly, we think, the basaltic grains that just deposit on the surface. The red, we think, are allotropes of sulfur. and the white are most likely sulfur dioxide frost. So SO2 gas is spewed out of out of the surface of the planet, and then when they deposit on the surface of the planet, which is about 140 Kelvin on the day side, it ends up being like white frost. Yeah, so yeah, the different colors are just different species of gas, different gases or grains of different sizes that deposit on the planet.
Very cool. Thank you. Could you simulate the elemental species of the plume based on the surface composition? And if so, would you expect to find a correlation with certain elements in the scattering brightness detected?
Yes. So I guess the problem, however, with that is that with the brightness that we see, the spacecraft's bandwidth is kind of in the visible spectrum. So gases or molecules that are not like bigger grains that have the same kind of size as the maybe hundreds of nanometers or micron level, they would not be detected by the camera at those wavelengths. However, if you add like a detector that's kind of like specific to maybe ultraviolet or even lower, then you can detect such. You can detect other species that are present.
Right, thank you.
Yeah.
Were any of the grains from this eruption event ejected out of Io itself, like out of the gravitational influence, or do they all settle back onto the surface?
They all for the most part, settle back onto the system. There are, however, theories that some of the gas on Io gets kind of like bombarded by the torus of the plasma of Jupiter. And when they get bombarded by the plasma torus, there can be ionization that kind of like allows the eruption on Io to feed the plasma torus. So you get, when those ionization events happen, you get the ions that are formed as a result carried off by the plasma. But only trace amounts.
Okay. And I guess sticking with that, how long would you expect the time to be from the particle to be ejected, go up, and then come back down?
About an hour, because so it's not really moving on ballistic timescales. So ballistic meaning like just under gravity, but because it's collisional, you have the material go up. If it's a gas, it has internal energy modes that's constantly being converted into translational if it doesn't lose it via radiation. But you get material go up really high, come back, but in the process of coming back, it's colliding with material that's also rising. So that kind of slows down the time it takes for it to come back to the surface, or like kind of like slowly traverse its way back to the surface. Yeah.
Very interesting. This is a clarification question. Is it the density and size of the particle in the ejecta, is that the most important factor in the brightness?
It's, yeah. So yes, the density and size, yeah. So if it's the right size and the right density, or you could have the right size of particles but not have enough of them and have more of another size. And that other size could not scatter as much light. And so it doesn't produce the profile that we expect to see. But if you have, like I said, the right size and the right density of the particles, then you can recreate the brightness profile that was seen. Yeah.
All right. Our last question will be about, we're bringing it all back together, so this one will include magnetic fields. Do the magnetic fields of Jupiter affect the shock above the volcano?
No, not directly. So, I mean, the magnetic field drives the plasma torus, right? Which moves at, I think, 53 kilometers a second or so. So when they bombard into the top of the canopy of into this region, pretty much the top of it, where you have gases present, they could then ionize some of those gases and are able to now those gases are ionized, they can move in a changing magnetic field and they can get carried away. But the plasma is not, from previous works, we found that it's not strong enough to significantly affect the plume structure. So.
All right, very good. Let's thank our speaker once again. And if you have any further questions, he's sitting right there. All right. So we're going to start the trivia process. If anybody has to leave and can't stay for trivia, I want to thank you so much for coming. We hope you had a good time. Please make sure, if you haven't checked out already, to be generous to your waitstaff. They do a great job with us in here. We love them for hosting us. For those of you that can stay for trivia, we'll come around with the trivia sheets. A reminder that the max group size is 4, and we won't allow cell phones. And we will start the trivia when I'm done eating my burger. No earlier.
All right. Everybody who wants to play has a trivia sheet, has some kind of writing utensil. All right. If you don't, too bad, so sad. We got our drinks. Michael finished his burger. And we have taken care of our humanly body necessities. Now let's get it rolling with question number 1. Famous astronomers. Which of the following astronomers was born in the 16th century? That's wrong. Okay, which one is it? Is it the 16th century or is it 1400 to 1499? Wait, everybody. Okay, born in the 15th century. Samuel.hart@sweary.org. We all know it by now. The numbers in the parentheses are right, not the 16th, but the 15th century. Which of the following astronomers was born in the 15th century? Tycho Brahe, Nicholas Copernicus, Galileo Galilei, Christian Huygens, or Johannes Kepler? And please only write the letter on your trivia sheet. It makes it easier for us to grade. We're just discussing the problem as it stands amongst each
Question 2, is everybody ready? All right. The Stars at Night, in the hit song Deep in the Heart of Texas, the Coyotes perform what activity? Is it A, rush around the brush, B, wail along the trail, C, ball and ball and ball, or D, cry when the moon is high?
Did you come up with these rhymes?
3 of 4 are from the song.
Oh, I didn't even realize that.
Oh, okay. 3 of 4 are from the song, but which one goes with the Coyotes?
I don't even know. I don't even think
The
I don't know
Coyotes.
anything beyond, like, I guess the chorus. Yeah.
Shout out to the former hockey team Arizona Coyotes. No, they moved to Utah. They're now the Utah Mammoth.
Utah what? Utah Mammoth?
Mammoth. Like
Are there
woolly
mammoths
mammoth.
in Utah?
There were at one
Are
point.
there coyotes in Arizona?
Yes. But yeah, no, I will miss them. They were a good team. Or they weren't good. I'm sorry, they were terrible, but they were fun. If they were a better team, they probably would still exist. It's just like the Atlanta Thrashers. You can commiserate. All right. I hope you picked the right rhyme time because we're going to move on to question 3.
We can come back if you need it. Question 3. Need for speed. Jupiter's moon, Io, is hauling tail during its orbit about Jupiter, boasting what orbital period? 2 days, 5 days, 10 days, 28 days, 70 days. Bonus. Wait. Okay. Please put this next to your letter. Do not put this in the bonus section. That bonus section will come into play at the end of the numbered questions. Put this next to your letter of question 3. What is the top speed in kilometers per second? In the inertial Jovian frame? Oh, yeah. No. Orbital period is orbital period. Like, what's the speed of its orbital period? That's not what I said, but maybe I should have said that. Well, you say top speed. Does it have a slow speed? You mean like perihelion and aphelion? So what's its speed at perihelion or perijovian? Perijove? Yes. No, minus 3 points for wrong units.
All right, I think I'm on. Yes. All right, question 4 is the 3 stars that make up the summer triangle are Vega, Deneb, and Altair. Rank their brightnesses. In order of brightest to. No, that wasn't one of them.
It counts. It counts.
No.
Hush, double drinking words.
To dimmest as viewed from Earth. In science terms, rank their apparent magnitude. Okay, so write the letters in the order that we ask you to.
Brightest to dimmest.
Brightest
So
to dimmest.
the one you think is the brightest goes first.
It's apparent. Let me. Apparent magnitude. So that doesn't mean the star. I mean, it's going to correlate to roughly the same thing-ish, but it's not star inherent. It's Earth inherent. How do we see those stars from Earth? Which one is the brightest? Which one is the dimmest? Fill that out. All right. We're going to question 5, but this is you. Why is this
yes.
sticky? Sorry.
Big, big lasers. The Laser Interferometer Gravitational Wave Observatory, also known as LIGO, has 2 locations in the continental U.S. Which 2 states house these big L-shaped observatories? And please mark both in the accompanying blank for question 5. Thank you very much.
Okay, we'll move on to question 6. And, music and astronomy. We always have a music question, so this one, let's work on it together. Which rock band produced the hit music album Music of the Spheres, featuring celestially named songs such as Alien Choir and Infinity Sign? Is it A, Green Day, B, Oasis, C, the All-American Rejects, D, Coldplay, or E, Genesis? Which one of these produced Music of the Spheres?
Does the infinity sign have a name? I feel like it should. Because like ampersand's like the and symbol. H sideways. Like Octothorpe is the hashtag, the pound symbol. Octothorpe, yeah. What's the name of the pound symbol? Okay, so pound, this is like a highly debated topic. Pound symbol and hashtag are colloquial terms for the symbol that is called the Octothorpe. And it gets super weird when you think about like generations. Because like we call it pound because that comes from England, because they would use that symbol for, no, I think it was for weight. The pound came from weight from England in like the 16 and 1700s, and then that got carried over when we had telephones for the pound symbol where you press it for the operator, and then we use it as a hashtag. I don't really know why it's called hashtag. It probably wasn't even, I don't even know when the Octothorpe came about, but yeah. Oh, the dollar? So that's a good question too. Probably dollar sign.
Big Ben.
Oh yeah.
No, I was saying we were the planners, basically, of it.
Why?
No, she was asking if I was going, and I'm like, well, yes, because I'm one of the planners. All right, are we ready for the bonus?
Wait, whoa. Does anybody need a question repeated?
Oh, yeah, that's right. I forget. 1, 2, 3, 4, 5, 6. Put the number up if you need a repeat.
All right.
All right.
Forever hold your peace. The bonus. This goes in the bonus section. Why do the moons of Jupiter outside of the Galilean moons receive no love? It's probably because they are glorified asteroids. Word. Anyway, name the 5th, 6th, 7th, 8th, and 9th largest Jovian moon by mass. By mass. Yeah, half point per answered. Hit. Number 10 is Carme. We're going to go through the answers. When you are done with your answer sheet, it will help us greatly if you come and bring them up. And please bring your writing utensil if we gave you one. We are an outreach service. We have no money.
No, I'm done. I'm booked.
Yes, if you are done, please bring your sheet up to us and your pen, please. We are an outreach service. That's not ours, sir. We take donations of pens as well. Thank you.
You can, okay, fine. You can announce third.
I just really want to say.
All right, everybody. We have graded
All right.
the results. We did not do so hot. Some others did hotter than us. But let's get on with it. What are the answers?
Oh, wait, but yeah, first we got to do the answers. All right, question 1.
Question 1, 1400 to 1499, Nicholas Copernicus
Yay, we got
with the
that one right.
heliocentric revolution. Brahe and Kepler were like contemporaries. Galileo Galilei was pretty late in the game, and then Huygens, I think, was like the latest. Well, he is the latest, but
Well, Galileo was with Kepler, kind of, if you see here. I mean,
I
he
guess they
was,
were also
yeah.
contemporaries. In my mind, they are not, but yeah.
Yeah, they were. But Huygens was the most recent one.
Yeah.
And Huygens was the one who was the namesake of the, because he discovered Titan,
Yeah.
so he got the name for the Huygens probe on Cassini.
Yep. Question 2 was about our song.
Yep, Whale Along the Trail. That's what the Coyotes are doing.
Who
deep
knew that? Who knew? I
in
didn't
the
know that.
heart of Texas.
You knew that because you looked it up, Sam. I didn't know that.
Wait, Sam, which one of these is not in the song?
Wow. I
Cry
thought that
when
one
the moon
was.
is high.
It rhymed with night. That's why I picked it.
Yeah.
Question 3 was the Need for Speed. 2 days.
It's really fast.
Really fast. Oh, and then 17 kilometers a second. Stupid fast.
It's technically slower than Earth, but it has to clear less of a distance than Earth does.
If someone can do the math, 2 pi r over, time.
Just pi r.
Well, 2 pi r or pi d.
Oh yeah, circumference is pi d.
Somebody do the math. Somebody check Sam's math.
All right. Question 4.
What's
Knowing
the math?
the
Wait.
basics.
Brian has the math. What's the math?
Oh.
Oh, okay. Yeah, it's about right.
Yeah.
Okay. Thank you, Pippa, for doing
Did
the...
you get the 2 days? Good for you. I did not know that one. Now I'll never forget, though. All right. The Vega, Deneb, and Altair. The order is Vega, Altair, and Deneb.
Cap.
Vega is the brightest, and I hope everybody got Vega as the brightest, because Vega is really bright. Vega is a very important star in the night sky.
It is 0.
Altair and Deneb, I can understand if you got them confused, but Altair beats it
I'm
out.
curious how close Altair and Deneb are. I feel like they're pretty close.
In magnitudes?
Yeah.
Yeah. We
Yeah.
can look it up. All right, 5.
And question 5 was about big old lasers. Louisiana and Washington. 2 of the randomest states you can think of. Also, all those states are pretty random, actually. Well, New Mexico has,
Los Alamos.
yeah. I was like,
And
big
the
bomb.
and don't they have the VLA? Wait, yes, right? No,
Maybe.
yes,
Yes.
maybe.
Yes.
Yeah. Thank
Thank
okay.
you, Mark. Nebraska has
I
corn.
remembered.
And then music and astronomy. Who was it?
It was Coldplay, a very recent album of theirs.
Chris Martin and the boys.
The Coldplay released Music of the Spheres.
Yeah, so they're pretty close. Well, half mag.
All right,
Yeah, no. Yeah.
now the bonus with the 5 next biggest moons beyond the Galilean moons.
To give
Of
Michael
course,
credit, he knew 2 of them.
I did.
I knew none of them.
I did.
Himalaya.
Himalaya.
The Himalayas. Amalthea, Phoebe, Alara, Pasiphae. 2
Yes.
of them have really good pictures. I wonder where those are from.
Right now it's a
Yeah.
big if,
Probably Cassini.
but if the Juno mission gets extended a second time, it will fly by Amalthea, because Amalthea is an inner Jupiter moon in the rings. It's close to the rings, so Juno might fly by it only if it gets extended.
If and only
So
if.
let's make sure it gets extended.
Scott just submitted, so
No,
Here's
no,
hoping.
it's close.
what's close?
The ascension.
Oh, yeah.
It just needs to get the seal of approval.
Yeah.
So let's get it across the finish line. All right,
Who won?
who won?
I
So
don't
we
know.
have
Who
our
won?
third place winner. Jasmine will announce our third place winner tonight, and they will be winning. Erica has the almanacs. Yes, they're 2024, but they have very cool stuff that's relevant always.
And
some
information.
LRO stickers.
Thank you. I asked to announce this one because I really wanted to say the name. Rings of Your Anus. Your Anus, yeah. Oh, great name. Oh, just bring it. Just bring it, yeah.
All right. Our second place winner will win a bunch of one frisbee, and a bunch of MMS foldable things. Yes, so very relevant to today since Kylie talked about MMS, and also some LRO stickers. We don't have MMS stickers, so yes. And the frisbee is Celestron. All right, the winner is Simon Mendenhall and the co-authors.
Gotta love those co-authors.
Look at you, just taking all the credit.
They told me to put that.
Really?
Yeah, I didn't even want to.
All right.
It was from the DPS abstract submission.
Our grand prize tonight is going to win a beautiful print that Robert donated to us a long time ago.
I
and
do believe
sat
it's
with
real.
us. I do believe it is a photo of Jupiter, probably taken by Juno.
Oh,
Or no, Voyager? Oh, from Voyager.
probably not Voyager.
It's color. It's probably Juno. Yeah. And then juice stickers, because this is the theme of our second talk about Io and Jupiter system. And the winner is, well, oh well, the Cosmospheria. Oh, my goodness. Oh, my goodness.
All roads lead to Hutchinson, Kansas. All roads lead to Hutchinson, Kansas. It's a phenomenon at this point. If you don't know about Hutchinson, Kansas, please, for the love of God, ask Caleb about it, please. All right, everybody. That do be the program, and that do be it.
All right. So, if I can get everybody's attention, please. We will hopefully see you all next on our June 4th AOT. That is the first Wednesday of June. I won't see you. I will be out of town, but the rest of them will see you. Until then, special thanks to Blue Star Brewery and UTSA. Please follow us on our socials, and thank you very much for attending.